Welcome to this Mathcast. In this episode, we're going to be looking at the idea of empirical probability and specifically a very important mathematical property or theorem called the law of large numbers. Let's start off with just a basic understanding of what empirical probability is. If I was to say to you that, and ask you to define what probability is, you would probably come up with a lot of formulas or something like that, but let's just keep it simple. Probability measures our belief that an event will occur. Most of the time when you or I talk about probability, we're typically talking about it in terms of theoretical probability, meaning if you were to flip a coin, it has a theoretical probability of 1/2 of the time being heads, 1/2 of the time being tails. However, the majority of things out there that involve computations on large data sets are usually done empirically, meaning that an experiment is repeated over and over and over again, and we try to figure out exactly how likely something is to occur by observing the number of times that it did occur. In this sense, empirical probability if you want to think of it this way, is akin to saying that believing is seeing. In other words, if you are asking me to tell you how likely something is to occur, I need to see that experiment happen several times to get a feeling for how often things occur. Now, because of this, we have to set up a couple of formulas here to look at the idea of empirical probability. And I'll just start off with the first one. To do this particular example, I'm going to suppose an experiment is run n times. Now, typically when we say something's done n times, what we mean is that n is the number of trials. So there are n trials to this particular experiment. And here's what I want to define for you today. I want to define the relative frequency of some event E. Now, this event could be a compound event, it could be a simple event, it doesn't really matter. I'm just saying that the event is something that occurred, or maybe didn't occur depending on the event, but it's some outcome that's possible from the experiment that we're looking for over the n trials. So what is the relative frequency? How do we define that? Well, the relative frequency is defined as the frequency of E, and this is sort of my own notation here, divided by n, which is the number of trials. So the frequency of E is the number of times E is observed. And n is the number of total trials. This is called the relative frequency of an event, and the idea is that this is some glimpse into the probability of that event occurring. Now, it's not exact, and we know it's not exact because if you consider, flipping a coin, we could perform 10 trials and see 10 heads, and we might think that the chances of getting a head is in fact 1 or 100%. But that's not entirely true. We know that in theory it should be a 50-50 chance, and just because something happens over a short number of trials doesn't necessarily make it true on the larger scale or for a larger picture. That idea is a very important idea. It's the way that we actually define probability in the first place. So if I want to change, and instead of asking you about the relative frequency of the event, what if I asked you about the probability of the event E instead? Well, it turns out that if I want to define the probability of the event E, I need to think long term. And the way that we do that is we think of it as a process where the number of trials gets bigger and bigger. We typically in mathematics we call that the limit. So this is the symbol here for limit, and all it means is the number of trials is getting bigger and bigger. So as the number of trials is getting bigger and bigger, we keep recalculating the relative frequency. That's the definition of probability. Now, this definition has an awfully lot to do with something called the law of large numbers. And let me give you just a short, brief summary of what the law of large numbers says. The law of large numbers says that as a random experiment is performed over and over again, the relative frequency of an event approaches the expected value for that event. What that means is that if I was to start flipping coins, I might not get a 50-50 split for my first 10 tosses. But as I continually toss the coin, I get closer and closer to that 50-50 split occurring. To illustrate this, I want to look at a small little graph and experiment that I've set up. In this graph, we're looking at two different things. We're looking at the absolute difference versus the relative difference of flipping coins. Now, let me explain what the absolute difference is first. Here, the number of coin tosses is 10. So in the absolute difference graph, what we're looking at is over the course of 10 tosses, how far away or how many more heads did we get than tails? For example, if you looked at it after 2 tosses, the difference is 0, meaning we had 1 head and 1 tail at that point in time, just as many. If you look at it at 4, there's a difference of -1, and the way that this graph is set up, that -1 means there's 1 more head than tail. So there's 1 more head than tail at this point, and then when you get over here to 10, there's 1 more tail than head. But the difference always stays between 1.5 and 1 the whole way through. Now, the relative difference is how we think of relative frequency, meaning it's going to take the fact that there is, at this point, when you look out at 10 tosses, that there is 1 more tail than head. It's going to take that and divide it by the number of tosses. So that's why over here you've got 0.1, because that's 1 out of 10. What's interesting about these two graphs is looking at what happens as these numbers get bigger. Let me change it to, instead of 10 coin tosses, let's try 100 coin tosses. If I repeat the experiment with 100 coin tosses, now instead of 10, the graphs change dramatically, but what I want you to notice is the absolute difference. We never have, at any one time, more than 6 or possibly 7 more tails than heads or heads than tails. They're all within 7 of each other. But if you look over at the relative difference, what's happening is that because of the large number of tosses as we go forward, even though there's larger absolute differences, the relative differences remain small. And in fact, the relative differences are going to 0. That's what the law of large numbers says. Let me move the slider just a little bit more here so you can see we're getting larger, a little bit larger here, more. Let me get a large number here. 7,430. If you look at the absolute difference graph, there's differences as much as 20, 22 at any one point in time. There might be 22 more tails than heads that you've counted up through that far. But you've actually tossed 7,000 coins. So having a difference of 20 is not all that big a deal if you've tossed 7,000. And in fact, if you look at the relative difference graph, in the beginning, there is a significant difference at some point, but as you go out, it's almost identically zero. And that is, in fact, what the law of large numbers is trying to tell you, is that the relative differences of those values approaches zero as the number of trials increases.